So yesterday I'm saying hello to everyone. I just do not see maybe gallery. Okay. Hello Sayed. Hello Hadassah. Hello Amir. Hello Mara. Hello Sarah. Hello Haley. Hello Lola. Hello Armor. Hello Vinjan. And hello Amar once again. It's like you're free to put camera on and off, but I prefer if cameras are on because I can read questions in your eyes and immediately adjust. So if there is no discomfort, it's a little better. So please raise hands who was at the meeting yesterday. 1, 2, 3, 4, 5, 6. Okay. So yesterday we did a little slow down because we invested time into recalling some background information about, what did we recall? Eigenstates and dot product, right? Did we cover anything else? I mean, not in the main line, but as a background. Haley, do you remember any subjects we covered, not in the notes, but as a background? Or only 2 subjects, right?
Orthogonality and sorry.
What did we cover yesterday in addition to like main class material?
Like Hadassah said, orthogonality.
Okay, orthogonality, which is connected to dot product, right? And concept of eigenstates, because we are going to use them today. So I will start showing slides like crazy, and let me check if anyone needs to leave literally at noon. So if I know our agreement and votes were for just 1 hour. So if you really need to leave at noon, if you were planning, just raise your hand so I plan accordingly. Okay. Yep. I'll try my best. So the several lectures that we are doing right now focus on the trick to separate variables, because molecular Schrödinger equation is not solvable. And our first step is to consider coordinates of ions, of nuclei, and coordinates of electrons separately, to treat them by independent equations. Objectively, they are not independent. So mathematically, rigorously, it is not possible. But we are going to use the fact that ions are much heavier, and at a time when electrons do a lot of rearrangements, nuclei change a little. And basically, I'm trying to spend about 3 lectures on this subject. Why this is needed? Well, first, any textbook on computational chemistry speaks about Born-Oppenheimer approximation, about separation of electronic and nuclear degrees of freedom. Second, if we do not model explosion, nuclear reaction, combustion, then if you do not consider charge transfer in the photovoltaic cells, if we look forward to characterize materials in the ambient conditions, then it is a very good approximation. So to think that nuclei and electrons are separate. And if we are thinking that our application may or may not, if it is questionable, if we go into extreme conditions, if there will be chemical transformations, then we need to assess how far can we neglect interaction between electrons and nuclei. So it is a very interesting and important effect, but in many cases it can be neglected, and we need to be aware of these opportunities, when to neglect and when not. I will show slides. I will skim through the slides that we did yesterday to those whose schedule were too busy. But briefly, what we are doing. I will try to say it by words because maybe it will go better. And then by showing equations, we will have a dual way to go through this information. So when we met on the previous week, and when you were doing homework, we were talking about five types of terms in the Hamiltonian, right? Different types of energies, like kinetic, potential, electron to nuclear. And we can select only those that relate to electrons and only those that relate to nuclei, and form two Schrödinger equations, one for wave function that depends on electrons, another that deals with wave function that depends only on nuclei. Then we take this two complete sets of wave functions, multiply them, and tell here is our approximate solution. So overall wave function of a molecule is a product of wave function for electrons and product and wave function for nuclei. This is not ideal, but it is practical. And we are going to discuss when and why this separation of variables is possible. So practically, we are doing the following. I will just repeat the words we were doing yesterday. So electronic wave functions form a complete set, good basis set. Then any function in the world can be represented as a superposition of these electronic wave functions. But the expansion coefficients in front of these basis functions will depend on whether nuclei are close or far from each other. And these coefficients that may depend on positions of nuclei are not known. So what we started to do, we represent overall molecular wave function as a superposition of all available electronic wave functions times the coefficients that depend on positions of nuclei. So we take this expansion and plug it into the complete molecular Schrödinger equation. When hello Hanmant, when we plug this equation in, we do know electronic wave functions, but we do not know things that depend on nuclei, and we solve for them. So it is a plan. And on the way, we need to get rid of electronic wave functions, and we were planning to get rid of them by the use of the concept of orthogonality. And therefore, we spent some time on not going like crazy through material, but making sure that we all are on the same page. So I promise that I will complete what we left from tomorrow and then go forward in analyzing what and when can be neglected to validate this separation. Any brief questions? Like maybe someone thinks that it is this material is not needed, or please let me know if general stream of logic seems reasonable, at least by now. Just show thumb up, thumb down. Good. Lola, you typed VGA. What does basis function mean? Okay. Anyone wants to volunteer and define basis functions? Okay, I'll try to do it right now. And maybe some of you will do it quicker than myself. Lola, and what do you think about Taylor expansion? Did you had it in the calculus?
Yes.
Okay, can you just briefly tell what it is? And it will bring us to the concept of basis functions.
I don't exactly remember what Taylor
But you've heard it, right?
looked like. Yeah, I've heard it before.
So please raise hands if you have heard about Taylor expansion before. And show if you never heard about it. Okay, so majority did hear about it. So basic any good function can be represented as summation of polynomial functions, right? So in the vicinity of a period. Do I have a blackboard on my back? So if we have, for example, exponential function, right? Do you see it, or it is not very visible? Exponential function. We can tell that in certain point, for example, in x equals 0, the e to the x in the limit x goes to 0 is equal to the value of the function at this point, which will be e to the power 0, right? Plus x, because it is linear here, plus x squared divided by 2, because then it changes its curvature. So complicated function can be represented as a summation of simple functions with appropriate coefficients. Lola, do you approve? Does it make sense?
Yes, it does.
Okay. Now, if I want to be general, I will write any function of x approximately equals to the value of this function at point x naught plus summation of coefficients Cn x to the power n, x maybe x minus x naught to the power n. So polynomials, the different powers from 0 to infinity in the vicinity of a point. So now in this expansion, this polynomial function, this power function, is our phi of order n of x. So it is a basis function. We use summation of set of functions to represent set of standard functions to represent any complicated function. And this set of functions, which in case of Taylor expansion is just polynomials, is called basis functions. Well, does it make sense? Is it better?
Yes, thank you.
Sarah, you raised the hand.
Yeah, can I add something?
Please do.
So I understand basis function as they are the functions, the addition of functions that represent my electrons in my system. So we understand electrons behave like a wave, and we have electron represented as using wave functions in Hartree-Fock or DFT. So the set of functions that represent these electrons represent either just the normal electronic behavior or polarization or diffusion or interaction between electrons and others features, depends on the accuracy of the basis set. So basically the basic set is that collection of functions. When I'm going to a higher basis set, that means I'm using more terms in my basis set representing more features of the electrons wave function. So
Thank you.
that's how I imagine it.
So what Sarah did a perfect comment, but she was speaking about computational chemistry only. The definition that we discussed here on the board is mathematical, is more general, applicable to any area of knowledge. And in specific case, if we are looking about electronic functions, then typically one, instead of these polynomials, one takes hydrogen-like atomic eigenstates. But we will get to it in maybe like 3 weeks from now. Okay, so time to, I need to finish in 40 minutes to match your schedule. So I'm not sure if I will see your faces while showing slides. So if there will be questions, please raise your voices. I'll try to look on the chat line, but I can get overexcited of the material and forget to respond appropriately. So based on your votes, we do lectures on Monday and Tuesday at 4 and 11. And the mandatory part is lab on Wednesday. So we are now yet in the first chapter, and we are spending a couple of meetings on Born-Oppenheimer approximation. Soon we will need to make presentations. So probably tomorrow we will make votes who wants to present what. And here are just a list of subjects from previous years. We were just voting. So just think ahead. Tomorrow we will practice voting, and I'll try to make amount of subjects either equal to number of attendees or half of the number of attendees to present by teams. Individual is better, but teams could be reasonable. In about a week, we need to complete another little homework with summarizing what we get in lectures, like give an equation of nonadiabatic term and maybe explaining what is potential energy surface. I will develop this assignment in more details and announce it tomorrow. And there will be a computational component of the homework, which will be very, very quick. It will relate to building of atomic models. So tomorrow we will start looking for the software to build atomic models, and the homework highly likely will be related to asking you to draw two structures. One structure when two reactants are separate from each other. It's just two different projections of the same system. And product when this molecule is adsorbed on a surface and formed chemical bond. So we will make our training tomorrow targeting to build models like this. Okay, so we do theory in order to predict properties of materials. Quantum mechanics is based on concept of eigenstates. We described example of hydrogen molecule and introduced concept of molecular Hamiltonian, which has 5 types of energies, 5 types of contributions, and we combined everything related to electron into one term. Then if we solve, here, if you solve for electronic wave functions, which are, let me see if I can draw. If you have electronic wave functions, overall wave function of a molecule, which depends on both electrons and ions, can be formulated as a summation of, Sarah, I saw your question, I saw your hand, summation of the basis functions with unknown coefficients. And we are going to plug this expansion into molecular Schrödinger equation. Yes, Sarah, please speak.
Professor, can we avoid Monday for presentation because I have Dr. Wenji lecture from 3:30 until 4:45, so I won't be able to attend all the lecture Monday.
I know of your restrictions, and I will arrange how to make presentations in such way so that it will follow your schedule. Either we will present on 2 days, or maybe we will sacrifice one Wednesday. But I'm aware of restrictions. Don't worry.
Okay, thank you.
Okay, so we are going to take this expression and plug it into the molecular Schrödinger equation. So this is the last slide where we stopped yesterday. And I'm going to go to skim through slides very quickly, but on this one, I need to make a little stop because objectively there are schedule conflicts. So let me attract your attention to everything which is written in a green color. So to save time, I will speak only myself, but for my curiosity, please raise hands if you feel that you can explain what is expressed in the green color. Like raise your thumb up if you can eventually explain, thumb down if you have no idea, and just wave a hand if you have general idea but not sure how to explain. Yeah, thank you, Haley. Thank you, Sayed. Thank you, Amir. Okay, thank you, Hadassah. Thank you, Hanmant. I'm curious about law. What is your, will you be able to explain green things?
Not completely, so I'm waiting.
Not completely, but I'm aware that it is something that your advisor will demand from you in a couple of days.
Okay.
Okay, so I'll do it right now, but the green thing has 4 lines, right? And it is an equation. First 3 lines is a left side of equation. Line number 4 is a right side of equation. We all remember that, so, and this is molecular Schrödinger equation. We know that molecular Schrödinger equation has quantum operator on the left and eigenvalue on the right. So quantum operator of Hamiltonian consists of 5 types of terms. But here you see there is a little circle about H electronic that I'm circling once again. So this one includes 3 terms, each of which relates to electronic degrees of freedom. So third line. The first 2 lines have terms related to nuclear part of the energy. And W in the 4th line is the eigenvalue. It's not an operator, it is a number. Now, in each line, on the very right, we have summation, then chi, which looks like X, and then phi, right? Summation chi phi. This is functional form of our solution of molecular Schrödinger equation. Phi is the electronic wave function that depends on positions of electrons as a function, and parametrically depends on positions of nuclei. And the chi serves as an expansion coefficient in front of these electronic functions. It does depend on positions of nuclei, and we are going to treat it as nuclear wave function. And absolutely the same expression is repeated again and again in each line. Capital. lower capital. So we assume that at this point we already know electronic wave functions phi sub a, and we do not know nuclear wave functions chi. We need to solve for chi, and we need to remove phi from our side, from our consideration. In order to remove phi from our consideration, we are going to practice a concept of orthogonality. So if functions phi form a complete set, if they are good mathematical functions, then they obey the orthogonality relation. So if we take one function, another function, and integrate over all values of electronic coordinates, the result of such product will be 1 if indices are the same, A equals B, and 0 if A is not equal B. So here we have two functions, and as a result, we have no functions, only numbers. So we want to practice this trick. And in order to practice this trick, we are going to use these little red boxes. We are going to multiply each green term by an additional red term, red box. So we will multiply on the wave function, electronic wave function with index B. And of course, it's always everywhere depends on R. I'm just lazy to write it. And integral over dr. So we hope that when B, phi sub B and phi sub A meet each other, the orthogonality relation will delete both functions. And we will have no phi and only chi. It will be the differential equation for chi that we can solve. Please stop me if you have questions. And if there are no, I'm going further. So I'm very poor in calligraphy, and from year to year, I'm trying to do the same thing again and again in different writing, but I fail. So you see, it is the same equation, lines first, second, third, fourth. The box with orthogonal function, the box with electronic function, and things related to nuclear wave function. So I like redrawing this image again and again, but here it is ready. So can you tell me what you see? Who has a brighter smile? So I see Hadassah is smiling and Sarah is smiling. Hadassah, can you tell how do you interpret this image?
I guess it's a play on the Greek letter sigma for some looking like a snake, and a Kronecker delta's made to look like a mouse. So
okay.
I'm guessing it's a play on the some taking care of the orthogonal elements.
Okay, okay, good. Is everyone follows or additional comments are needed? Amara? No, Sarah was smiling. Sarah, would you please share your vision what this image is?
I think she said everything, but yeah.
But tell by your own words.
Okay, so here's a sigma is just a drawing in a cat face, and then the submission, this sign that adds all terms of sigma together are just in a mouse shape. So yeah,
Okay.
so here basically we're adding all the sigmas we have a lot.
Okay, yeah, thank you. So when we practice linear algebra in not as drawing big matrices, but just by playing the summation things, right? Delta function, Kronecker delta, this delta sub AB, is just a matrix with ones on the main diagonal. And if this matrix is attacked by sigma, by summation sign, this identity matrix disappears, right? So therefore, this snake, it's the mouse or whatever. Okay. So whenever we have this phi b, phi a multiplied and integrated, we get delta AB, which is just matrix with 1, 1, 1, 1, and zeros everywhere else. And here is the summation. Here is a delta function. We are looking to have this term canceled. Here again, we have phi sub b, phi sub a. It will generate our delta. Through orthogonality, we have summation. It's going to be canceled. Here we again have product of two functions with different indices. We have the integral, so it generate delta function, and upon summation, it will be erased. As a price for this eraser, anything that was staying between delta function and summation will change index. Like it was index A, now it will get the index B. So it was A, now it will get index B. So terms second, third, and fourth line are very mathematically comfortable. We are good to go with them. But the line number 1 is special, and it needs special treatment. And this is a biggest problem and biggest chance for discoveries. So here I have removed everything related to electronic wave functions for the second, third, and fourth term. And they look like an equation for chi sub b that we are ready to solve, right? But in the term number 1, you see, I didn't dare, I was not ready to move this phi electronic function through the operator of kinetic energy of nuclei. So I still have operator of kinetic energy of nuclei between them. And this kinetic energy of nuclei is special. Why it is special? Anyone is ready to recall, to remind for all of us, how does operator of kinetic energy looks in differential form? Just raise your hand if you have idea what it is, or show thumb down if you have no idea, or wave your hand if you've heard before but not sure how to explain. So how, yes, thank you, Hadassah. Anyone else? How does operator of kinetic energy is expressed in differential form? Just show if you're absolutely uncomfortable, show down. If more or less, show in between. Okay. Hadassah, would you like to try?
Sure. Kinetic energy can be represented as momentum squared over 2 multiplied by the mass, and then momentum, since it's mass times velocity, you could have the second derivative, the first derivative of the positions.
Mm-hmm. Yes, yes. Yeah, thank you. It's absolutely correct. I'm very happy with your answer. Thank you. So let's see what I have. I just need an empty space somewhere. Okay. Let me quickly add an empty slide, and then new slide blank. Let's go ahead. So I'm just carefully writing down what Hadassah taught to me. So kinetic energy for nucleus is, well, we do summation of all nucleus, mass of a nucleus, velocity of a nucleus squared divided by 2. And we can replace it by momentum of nucleus squared by 2 mass of nucleus I. Now, the summation masses can be taken care of anytime. What is most important, that momentum, and Hadassah, please correct me if I'm wrong, I'm always making errors with science, is proportional to derivative over position. So if this equation is a challenge, let me know and we will discuss when we have a little more time, because now I need to rush through and get some material. But do not forget, make a note in your notebooks if you're taking notes. This is one of the fundamental equations for quantum theory, and we need to discuss. It's quite simple, but there is a lot of philosophy. So momentum is related to derivative over position. And if you have momentum squared, if you plug it into here, then it will be second derivative, d2 over dri squared. And then we take care of all factors and summations. So this is very important, because when we do have our chi a of r, phi a of electronic and nuclear, here we have phi b of r. And if in between we have a second derivative over r squared, it means that before we can apply orthogonality for this term and this term, the operator of derivative will change the nuclear wave function and electronic wave function. And this fact may affect orthogonality. Like even if the functions have different indices, A and B, the result of this operation may not be zero. So this derivative over position of ions that stemming from kinetic energy of nuclei does make sense. I will repeat several times, just telling it right now. This kinetic energy of nuclei is important only if nuclei have kinetic energy. If you have frozen, if nuclei do not move, then this term drop and everything is good. So the higher the temperature, the higher the velocity or momentum of each nucleus of each atom, the stronger this term is. When they do not move, this term can be dropped and everything is simple. When it is big, then we are going to regime of combustion and explosion and fun things. Okay. And this term related to this kinetic energy of nuclei is a key point of theoretical background for future doctoral thesis of Lola and Haley. I will stop talking about it on our next lecture, but you will need to talk about it for several years. Okay, so terms, kinetic energy, and now I will go through this thing, but it would be a very appropriate time to practice a little bit of calculus, a little bit of taking derivatives. So the second derivative here is applied to a product of two functions. And we can do this second derivative as subsequently, making the first derivative of product of two functions and then second. So I'm absolutely sure you all are comfortable with taking derivatives, but let me just ask so that you confirm that taking derivative of a product function is a natural thing and you can easily do it. Right? You do not worry. This class is not on calculus. We will do just practical run of software. If you do not know something, just let me know. I will cover. So yes, if you're comfortable. No, if you're absolutely discomforted, more or less if you heard, but do not want to do it for a grade. Okay. So anyone is very discomfortable with derivative of a product? No one. It's good. Yeah, thank you. So when we do have product of two functions, the derivative is we do derivative of first, keeping second unchanged, and then there appears another term where a first function is unchanged, and we apply derivative to a second term, right? And then we need to apply the derivative once again. And then since we already got two terms instead of one, when we apply derivative once again, there will be total 4 terms. So first term will be applying derivative twice to the chi function that depends on nuclei. Last term times phi. Last term will be second derivative applied to the electronic function phi. And in the middle, there will be 2 cross terms where first derivative is taken either to both first derivative of chi and first derivative of phi. Please attract my attention if you disagree, if it looks suspicious. If you're fine, just do not give any signal. You'll get forward. Okay. So when we were doing in previous years, and there were some people in class, I was asking someone to come and derive it, but we can skip it for this year. So when we are practicing these derivatives, we do see that for the very first term, where derivative is applied only to nuclear wave function, we can consider it as kinetic energy operator is applied only to nuclear wave function, and electronic function is unchanged. We can even do swap their order. And for the first term, we can do the same trick as we did for other lines in the equation. So we can apply orthogonality relation and get rid of the wave function. This result of this chain derivative brings us back to second derivative of nuclear wave function, which looks like regular things, pure. And there is a term, it's called pure kinetic energy. So pure nuclear kinetic energy. So it is good, dream term, no problems. Other 2 terms are problematic. They show how electronic wave function phi is getting changed when nuclei are contracting or expanding. So it is response of the electronic wave function to motion of nuclei. It is our natural wish and desire to drop these terms as much as possible. And if we do not have explosion and combustion or electron transfer, we can drop them. But sometimes we cannot. So there is a terminology. The name for this term is so-called non-adiabatic coupling. And this term combines wave function with index B and electronic wave function with index A. So basically, it is responsible for the rate of transition from one electronic state to another electronic state. It violates one of the postulates of quantum theory, because here system is not isolated. Okay, so for terms 2, 3, and 4, we can apply delta function and simplify things. For pure kinetic energy, we still can apply delta function, but for the non-adiabatic term, which includes these derivatives of electronic function over positions of nuclei, the orthogonality relation is not applicable. Therefore, it is a special term. And if non-adiabatic term can be dropped, we just tell we drop it, and we are in the adiabatic representation. We just look at low temperature properties of materials. If it cannot be dropped, it's completely different theories. So all publicly available and commercial software do not take into account of non-adiabatic couplings. If one needs to describe them, then it is some homegrown codes. And in the course, we will do without this term. So if this term is dropped, then we have two equations, one for electronic part that generates phi sub A, another is for nuclear part, for chi sub B. The energies, eigenstates of electronic things come here as additional term that contributes to nuclear repulsion potential term, and summation of these two terms are referred to as PES, potential energy surface. Okay, time is about over, but we are done with review of previous lecture and start the new one. So the concept of non-adiabatic couplings is really nicely explained in the book by May and Kuhn, and I am aware of it because Dr. May was in my thesis committee in 2000. It is what we already did. It is, no, I need to go forward, not backwards. So there will be a couple of slides providing the same thing, maybe in a better typing. So nuclear and electronic wave function, applying derivatives, having total 4 terms. And one of them is pure, where derivative or position of nuclei is applied to nuclear wave functions, and other are mixing. So conditions, strong laser, electron transfer, photo-induced reactions, plasma, very hot, and I didn't didn't mention explosion. And fragmentation may be induced by strong laser, like photoreactions. Like in Star Wars, if characters are fencing with lightsabers, definitely it's a non-adiabatic process. So first term included pure kinetic energy, and this mixture terms which relate to non-adiabaticity that we neglect in Born-Oppenheimer approximation. If we want to carefully treat these terms, and most of us are going to drop these terms and forget about them completely. Some of us may deal with research of like combustion, explosion, and electron transfer. So it's worth of giving notations. So summation, I think it should be only over A, of non-adiabatic coupling times nuclear wave function is everything we had here. So derivative or positions of ions applied to nuclear wave function, derivative or positions of ions applied to electronic wave function. So here we have the first derivative, first order response of the electronic wave functions to change of interatomic distances. This term is bigger than the top one. Here we have the second order response of electronic wave function to nuclear positions, and overall non-adiabaticity is considered by 1% of researchers, and this second order correction is 1% of 1%, like 10 to the -4 researchers look at this term. So it's often dropped even if one goes to explosions and combustions. Okay. There is another little thing that is worth mentioning. When we process this non-adiabatic term, we notice that there is a first derivative of the nuclear wave function or position of ions. And thanks to Hadassah, we remember that derivative of a nuclear position is, with some proportionality coefficients, is operator of momentum. So if we play a little bit, multiply and divide by appropriate factors, we can treat this green circle as momentum operator of nuclei. And in this representation, non-adiabatic couplings can be in an oversimplified, shorter form written in the following way. So matrix element of the derivative of position between electronic terms going from A to B multiplied by momentum of nuclei. And this notation highlights once again that if momentum of nuclei is 0, then there is no non-adiabatic coupling. So it increases with increase of kinetic energy of nuclei. Okay. And then we finally drop this non-adiabatic term, assuming that our temperature is low and we have only good regular terms. So this, I have 1 minute more. So summation of nuclei to nuclei repulsion and electronic eigenvalues are different depending on which state electronic system is. If all electrons are in ground state, then dependence of the energy of interatomic position has one minimum of equilibrium and one curvature. If we excite system, the potential curve, the dependence of this VNN plus EB is changing, and it may lead to different equilibrium position. Or sometimes if we excite it higher up in energy, there could be no equilibrium at all, which means we photoexcite molecule and it breaks on pieces. Again, it's like laser weapon. You shine on something with high intensity laser and things disintegrate. So interatomic bonds break. So this was the concept of potential energy surfaces. And I think it is, since some of us need to depart, I suggest we stop here. Thank you for attention. I will get used to our schedule, and it's possible to squeeze all lectures in a given time, which we will get right. There is only a few things left. Okay, meeting is done. Anyone is welcome to disconnect. I'll stay here to answer questions if any, and looking forward to see you tomorrow in the lab.
Thank you.
Thank you. Special thank you for active discussion.